Section 4.4, how about a little more mean value theorem? Yes, we have mean value theorem for derivatives, and now we're going to have it for integration as well. Recall, just real quickly, the mean value theorem of derivatives tells us that if we have a function, and we have 2 points, a beginning point and an end point, an a and a b value, that if we draw in that secant line, then there's some c value between which the derivative or the slope of that tangent line is equal to the slope of the secant line. So again, we had 2 endpoints, we found the average rate of change equal to the instantaneous rate of change at some point c, and c was in between a and b. What does the mean value theorem of integration tell us? Well, it tells us that there exists a rectangle between the inscribed and circumscribed rectangles that has the exact area of that region under the curve. And when we did our estimations, we'll go back to this again. Yeah, we might as well. So remember, we estimated x squared plus 1 between 0 and 4, right? And we cut it into 4 parts, and we did the inscribed, circumscribed, midpoint, trapezoid, all those wonderful formulas. And we talked about the lower sum and the upper sum, didn't we? So if we go from here to 0 to 4, drawing a graph there, we know that we have this area in this region. That's what we're looking for ultimately. That's what the integration from a to b of f of x dx means. We're finding that area under the curve made with the x-axis. What the mean value theorem tells us is that if we have this a and b, these upper and lower boundaries, that if we create the lower sum, so if we just do the most basic of lower sums, we're taking the lowest value, this will be this region here, and we found the upper region, the upper circumscribed rectangles there, that would be this big rectangle here. We know that there's some c value in between a and b. There's some c value in here, so if we found the area of this box, then we would have the area of this region under this curve. We also call this the average value theorem. Mean, average, yes. So average value theorem, mean value theorem, they're going to go very closely with each other here. So we know then that if I integrate this function of x from x squared plus 1, then there's some value c here. So if I create a rectangle, and it's going to be between a and b, or my lower and my upper bounds, this rectangle in here is going to be the same as the integration. Well, how do I find the area of this rectangle? Well, I found it by finding my value, so f of c, and multiplied it by my delta x. In this case, my delta x was 4, so I went from 0 to 4. And that's what we're going to see up here. We see that the integration from a to b of f of x dx is equal to some c value, f of c, times the distance from my upper to my lower bound. So what's that going to look like? Well, here we go. Here's our example. Just like we did with mean value theorem of derivatives, for derivatives, we can find the actual c value. So here's my function, 2x minus 1. We're on the interval from 1 to 5. So can we find that c value in which the area of the rectangle is going to equal the actual area of the figure? So that's going to look like the integration from a to b, so from 1 to 5, of my function, 2x minus 1 dx. And that's going to equal my f of c, which we don't know c value yet, times my delta x, my 5 minus 1. I'm looking for c. Well, if I go ahead and plug in my 5, or find my integration first, I guess. So we get x squared minus x from 1 to 5. And that's going to equal 4 times f of c, isn't it? All right. So we're going to go ahead then, plug in your 5. So we have 5 squared minus 5, which is going to be 20. Plug in my 1, I get 1 minus 1. Hey, that's 0. That kind of works, doesn't it? And that's going to equal 4 times f of c. Well, 20 minus 0, that's going to give us 20. I'm going to divide my 4 over. and I'm going to end up with 5 equals f of c. So I want to know, when does f of c equal 5? Well, how do I find f of c? F of c, to find it, I need to go ahead and plug c in for my x values, wherever I see an x in my f of x function. Running out of room there, so we have 2c minus 1 is going to equal 5. Go ahead and solve for c. We add 1 and divide by 2, so we get c equals 3. So what does that tell us? Well, that tells us that if I were to graph 2x minus 1, which hopefully most of us think and know that it looks like this, that the area between 1, if we gave 1, it would be 1, so it would be over here a little bit, and 5. If we look at this region, I'm going to go a little higher here. This area of this region here, the area of that is going to equal the same as if I came over here to 3 and created a rectangle in this form. So the area of this rectangle is going to equal the area of this, and we know that that's in a trapezoid form. So we can find the average or the mean value point that's going to occur when x equals 3. Very important as we get into the average value. And we know that the average value is very important. It's going to come up almost all the time on our AP exam, and that's what we're studying for. We're going to make sure that we understand the mean value theorem, which is actually our average value of a function. The average value, if I take that f of c, remember our definition was the integration from a to b of f of x dx equals our f of c times b minus a, isn't it? That's our mean value theorem for integration. Well, if I divide by b minus a, since there's no variables in there, I can bring this b minus a to the outside. So I have 1 over b minus a integrations from a to b of f of x dx is going to equal my f of c. So I'm going to know the average value of that function is going to be 1 over b minus a times the integration from a to b of f of x dx. What's that going to look like? Well, I just happen to have an example. So find the average value of f of x equals 2x squared plus 3x on the interval from 0 to 2. So again, my average value, I have 1 over b minus a. B again is my upper bound. A is my lower bound. So you might want to put that up there again. A is the lower, b is the upper. So we have our 2 minus 0 integration from 0 to 2, again, always a to b, of the function 2x squared plus 3x dx. So we have a half integration from 0 to 2 of 2x squared plus 3x dx. I can go ahead and integrate that. Integration of 2x squared is going to be 2/3 x to the third plus 3x squared over 2. Again, I'm going from 0 to 2. Since there's no variable out here, we can kind of leave that 1/2 out there and plug in our 2 and plug in our 0. So here I have 2 to the third, which is 8, times 2 gives me 16/3. Plus, when I plug in 2 here, I get 2 squared is 4, times 3 is 12, divided by 2 gives me 6. Minus, plugging in my 0, I end up with 0. And I would highly recommend and suggest that you always put in what that value is, even though it's going to be 0, just because some of our problems are not going to end up being 0. And sometimes you think, oh, it's just 0. Well, go ahead and plug it in and make sure. And put in that 0 to show that, yes, you did go ahead and plug that in and you don't question it in your mind. I'd hate for you to lose a point there just because you thought it was 0 or you didn't remember to put it in or something of that sort. So here we have, what, 18/3. When I go ahead and add those together, I end up with 34/3. Multiply my half into there, so I end up with 17/3. And that's going to be the average value of that function, is 17/3. So if we look at the calculator again, we can go and do our math, and 9, and we can type this in. Before we do that, I'm going to type in my 1/2. So I have 1 divided by 2, then times math 9. So I have a half of the integration from 0 to 2 of my function, 2x squared plus 3x dx. Enter. And we end up with, hey, look at that, 5 2/3, which is 17/3. So, what does that tell us? Well, maybe I should go back there as well. Just in my mind, I think I didn't clearly state what that was. So, what does that tell us? If I look at 2x squared plus 3x, so that's going to look something like that. I don't remember if it goes. It should go below the x-axis, shouldn't it? Should go through 0 as well. Oh, that was bad. Just kind of roughly doing that. So if we look from 0 to 2 here, then the average value, f of c, my c value in here, we don't know what that c value is. We could find it, but it's going to equal 17/3. So f of c is going to equal 17/3. So that's kind of where that rectangle is going to be created in there, if that makes sense. All right, and that's going to be the average value of that. All right, so if you have questions, let me know. Good luck. Gives you an idea of where the mean value theorem for integration is, and what it is, and where we're going to use it. Good luck. Enjoy. If you have questions, let me know.